All right, let's get you ready. I know your big deep learning exam is just around the corner, and we need to tackle one of the trickiest topics out there, explaining black box models. It's one of those things that can really trip you up, but don't worry, we're going to break it all down so you can walk into that exam feeling totally confident.
Okay, deep breath. The exam's tomorrow. Let's not waste any time. One of the biggest, most important topics you are absolutely going to face is model explainability. It all comes down to this. What happens when our super powerful AI models make these incredible decisions, but we have literally no idea why? It's like having a genius who gives you amazing answers but refuses to show their work. And that's not just a puzzle, it's a huge problem. Let's unpack it.
So here's our game plan. We'll start with why this black box thing is such a big deal. Then we'll get our key terms down. After that, we'll cover the 4 main ways to explain these models, look at the actual tools you use, and then we'll wrap up with a final review sheet to lock it all in. All right, let's dive right into the core of the issue. So we can build these amazing AI models that are incredibly accurate, but a lot of the time, their internal logic is a complete mystery. It's a black box. Now, this becomes a massive problem when we start using these models in the real world to make decisions that affect real people's lives, and they get it wrong for reasons we can't even begin to understand. Let's look at some classic examples. Okay, you'll definitely want to have these examples in your back pocket for the exam. These are the greatest hits. You've got a crime prediction model that was biased, an Amazon algorithm that just stopped delivering to certain neighborhoods, and then my favorites, which are just mind-boggling. A military model that thought enemy tank was just another word for a cloudy day, and another one that couldn't tell a wolf from a husky. It was just looking for snow in the picture. In every single one of these cases, the model found a shortcut, a cheat, and it was completely wrong. That's the danger. And here's the really big takeaway, okay? This isn't just about some weird bug in the code. This is a huge societal problem. When the logic is a secret, really bad things, like discrimination, can get baked right into the system, totally hidden from view. That's why this is on your exam. It's that important. Okay, so we get the why. Now let's build up our vocabulary for the how. You know how exams are. You have got to know the terminology. So pay close attention here, because these definitions are prime exam material. First up, the big one, interpretability. Honestly, the easiest way to think about this is that it's a translator. It's a bridge that translates the super complex machine logic into plain old human language so that we can actually understand what on earth is going on inside that model.
Now, this right here is a super important distinction. You have to know the difference between global and local. Think of it like this. Global is like being a master mechanic who understands how a whole car engine works, every single part. Local is just asking, why did my check engine light just turn on? You don't need the full engine blueprint for that. You just need to know what happened right now. Big picture versus a single event.
And finally, we have the desiderata, which, is just a fancy academic word for the wish list of what makes for a really good explanation. It's not enough for an explanation to just sound good. It has to be accurate. It has to have high fidelity, which just means it's being truthful to what the original model is actually doing. And then, of course, you have the really big ones. Is it fair? Does it protect people's privacy? All of that is what builds trust. Okay, so we know the problem, we know the terms, so how do we actually do this stuff? Well, the easiest way to remember all the different methods for your test is to think of them as 4 different ways to approach the problem. Let's walk through them. First, we've got the model explanation problem. The goal here is pretty ambitious. You basically build a stunt double for the black box. You create a second, totally separate model that's way simpler, maybe just a set of if-then rules, but that acts just like the original complex one. This is how you get that global, big-picture understanding we were talking about.
The second approach is the outcome explanation problem. And if that last one was global, this one is completely local. Here, we don't care about cloning the whole system. We just want to know, why was this one person denied a loan? That's it. It's focused, it's specific, and it's often a whole lot easier to do.
Third up is the inspection problem. The best way to think of this is like a mechanic hooking your car up to a diagnostic computer. They're not building a new engine. They're just running tests on the original one, poking it, prodding it, feeding it different inputs, and using visuals to see how it reacts. It's all about understanding the original model directly.
And number 4 is transparent design. And this one kind of flips the whole script. It basically asks, hang on, why are we making this so hard on ourselves? Instead of building a complicated black box and then struggling to explain it, why not just build a model that's easy to understand from the very beginning, like a simple decision tree? The big trade-off, of course, is that sometimes these simpler models just aren't as powerful. Okay, so those are the 4 big picture ideas. Now let's get practical and talk about the actual tools you'd use. This is the stuff you're likely to see specific questions about, so let's get familiar with what's in the toolkit. So here are the main players. You've got decision trees and decision rules, which are basically just flowcharts. Then there's feature importance, which just ranks what inputs matter the most. For things like images, you have saliency masks, which are super cool. They create heat maps that show you exactly what part of the image the AI was looking at. And then prototype selection, which is pretty intuitive. It just says, I made this decision because this new thing looks a lot like these other things I've already seen. And this is a perfect side-by-side. On the left, you see a decision tree. It's a step-by-step path to an answer. On the right, that's feature importance. It's not a path, it's a ranking. It doesn't tell you the how, it just tells you the what mattered most. In this case, for surviving the Titanic, gender was the #1 factor. 2 completely different ways of explaining the same model's prediction.
Okay, time for the final review. Let's bring it all home. Seriously, if you're going to take a mental snapshot of any slide, make it this next one. This is your cheat sheet. This connects the 4 big problems we talked about with the tools that are used to solve them.
Just take a second and let this sink in. Look at how for the global model explanation problem, using a whole decision tree makes total sense. But for a local outcome explanation, something more focused like feature importance is the right tool for the job. This table connects the problem to the solution. If you get this, you are in really great shape for the exam.
So to wrap it all up, let's just zoom out for a second. Everything we just covered, it's not just theory you need to memorize for a test. It's really about the future. It's about whether or not we can build artificial intelligence that we can actually trust with really important decisions about our health, our money, and our safety. If we can truly open that black box, it changes everything. Okay, you've got this.